So welcome back to the next section. We're going to start our discussion today by describing parallel programming concepts. If you recall, last time we had talked about concepts related to concurrent programming, and now we're going to talk about parallel programming. So we'll start out by talking about some of the key concepts in parallel programming, and as you'll see, they have a lot to do with the idea of divide and conquer, taking a big problem and to break it up into smaller chunks. We're also going to give you a little bit of an overview of when to apply parallelism. And of course, the very pragmatic answer in this class is when you should apply parallelism is when you do the programming assignments that deal with parallelism. But more generally, there are constraints and situations under which parallel computing is the right thing, and there are other situations where it's the wrong thing. So we'll talk a little bit about this. We'll cover this in more detail later when we get into the nuts and bolts of parallel programming with Java streams. So what is parallelism? Parallelism is a form of computing that performs several steps on multiple processors or multiple processor cores. Back in the day, 20, 30 years ago, we typically had multi-processors where each processor had a single core and you would have multiple processors on a system. Nowadays, it's much more likely that you'll have multi-core processors where one processor has multiple cores. And of course, you can still have cluster computing where you can have multiple processors which have multiple cores. So there's lots of different variations that are out there at this point. There's a series of steps that are used in parallel computing, starting with what's called the splitting step. Remember I said earlier that parallel computing is about divide and conquer. So the first step in parallel computing is to take a task and partition it up into multiple subtasks. And if you play your cards right and you're using the right data structures and the right circumstances and the right kinds of data, you'd like the splitting to be efficient. You don't want to spend a lot of time splitting, and you'd also like the splitting to be even as much as possible, because that ends up with chunks that are pretty much the same size, and you'll see why that's an important thing in just a bit. The next phase in parallel computing is called the apply phase, and that's where we're going to take the various chunks that we've created, the subtasks from the splitting phase, and then run them independently in parallel. So as you can see here, we've got a bunch of things that are going to be running in parallel. And my nomenclature here is little squiggly thread-like things with an arrow. That's a thread. And then the little apple cores are cores. Right here you see we have the same number of threads as there are of cores. That doesn't have to be the case, but it's often the case. Each of the subtasks, the things you see here, kind of like the little circles, those are going to be, or it's not the circles, where it says process sequentially. Each of the subtasks runs sequentially within itself, but together in the aggregate, all of them run in parallel. So each individual task is running, doing its thing sequentially, and ideally in isolation from anything else that's going on. We'll talk more about that later. And all those sequential tasks are all running at the same time, and then they will all run in parallel because they're all running aggregate or together in parallel, but each task or each subtask is actually sequential. The third and final stage in this is called combine, and it basically takes the sub-results from the subtasks. So each of the things, as you were running sequentially, you got a result from that, and then they get successively joined into a so-called single reduced result. So as you can see, first we'll take, pairwise subtasks that finished, and we join them, and then we take another pair of subtasks that finish, and we join them, and then we take the results of that, and we join that. And there could very well be sort of, log n worth of these joining steps going on, or the depth of the tree of joins or log n. And that is why you want things to be split evenly, because then you will have a much faster time to join them together. The key goal of parallelism, or a key goal of parallelism, is to efficiently partition or split the tasks into subtasks and to efficiently combine them back together again or join them back together again. If you can't do the splitting and the joining efficiently, well, then it's going to be a little harder. So you can basically think of parallelism as an optimization, the goal of which is to improve performance. And if you want to learn more about that, there's a great link at the bottom of the slide by Brian Getz, who's one of the chief architects of Java, written a great book together with some colleagues on Java concurrent programming, and he has a number of excellent various web articles and videos and so on that talks about how parallel computing can work in Java, or does work in Java. So when we talk about performance, what we're really concerned primarily here is with throughput, scalability, and latency. So throughput is basically how much work you can do in a given unit of time. Scalability says as the number of tasks grow, does your system continue to increase to be able to handle them in a graceful way? And latency is really a measure of delay. How long does it take to start something? How long does it take for something to finish? And all those are interesting dimensions, and the goal of parallelism is sort of to improve them all. And we'll talk more about that in just a bit. So the next question that's worth considering is, when should we apply parallelism? Should it always be applied? So parallelism works best under certain conditions. One condition is when the tasks that are being split up into subtasks are independent of each other. And this is often gives rise to a form of parallel computing that's known as embarrassingly parallel, which is a funny term. The best way to understand this, a lot of people who aren't native English speakers are like, what's embarrassing about this? Why is this embarrassing? And probably the best analogy I can give is the term embarrassment of riches. Someone is so rich, like Jeff Bezos or Elon Musk, that it's embarrassing. So they're embarrassing of riches. So embarrassingly parallel, it just is a way of saying that the tasks or subtasks that are going to be running have little or usually no dependencies or need for communication between them in order to be able to get their work done. And there's no sharing of results. Everything's running independently of each other. The classic example, which is why we have a picture of washing machines here, is doing loads of laundry. So each load of laundry runs independently of the other loads of laundry. And so as a result, as long as you have enough washers, you can wash all your clothes in parallel. So there's no dependency between one load to another. So that's an example. If you ever think of embarrassingly parallel, think of going to the laundromat after a semester's worth of not washing your clothes and washing them all at once, and you can finish them all very quickly. Okay, another situation under which parallelism works very well is when there's lots of data and lots of processing to perform. If we only have a very small amount of data or a very little amount of processing, there's really not a lot of benefits of parallel computing. In fact, it turns out you can actually make things run slower because of the overhead of partitioning or splitting and combining and joining. So it could actually be worse if you don't have this condition hold. So here's a way to think about this in a graphical form. This is called the NQ model. And again, if you go take a look here, you can learn more about the NQ model. So basically the idea is N is the number of elements to process for each of the threads or each of the independent cores that is running. So obviously we'd like to have N be large, because then we're getting a win from parallelism. And the other one is Q. And Q is a quantification of how CPU intensive the processing is. So if you have a lot of work to process, for each data element, you have to do a lot of computation, like you're trying to do a factorization of a large prime number or something like that. Or you're trying to break a password using some kind of decryption algorithm or whatever. Then if Q is large, in other words, the amount of processing is high, then you're going to get a bigger win from parallel computing. So the ideal situation is when N and Q are very high, and the less than ideal situation is when N and Q are very low. Another situation here is when the threads neither block nor share mutable state. And this is something that's very important. We talked about embarrassingly parallel computations. What that means is there's no sharing. Sometimes there's a little sharing. So a good example, in fact, one that's relevant for your programming assignments, is the use of a cache. So we have not a hardware cache, but we have a software cache in the program that caches the images that are downloaded from remote web servers and processed and then transformed and so on. So we have a cache. And the threads have to go check that cache to see if they've already got the image that's downloaded. So that's an example where there's a little bit of sharing. And so if you're going to have some sharing, then you'd like to try to make the sharing as little as possible. So ideally, threads neither block, that is, they don't wait for I/O, they just continue running till they're done, and they don't have any shared mutable state. Sometimes you can't quite get there, but if you can, that makes it more ideal. In fact, Java really focuses on this from a framework point of view. They have a really cool framework called the fork join pool framework. And the fork join pool framework is designed for tasks that run independently. And they also use this really cool technique called work stealing. And we'll talk a little bit about the fork join framework and a little bit about work stealing, although that's really a topic that's covered more in my sibling course that comes in the spring semester. So fork join takes big tasks, breaks them up into small tasks, and then runs them together in parallel in the fork join pool. And work stealing basically says if one thread in the fork join pool doesn't have any work to do, rather than just go to sleep or spin idly, it goes and tries to steal work from other threads that have too much work. So that's what's called work stealing. And again, we'll talk more about that. I don't expect you to know much about the fork join framework or work stealing yet. We'll cover that a little bit later. And of course, another place where you get a big win from parallel computing is when you have many cores and or many processors. If you only have one core, you can certainly do a little bit of parallel computing, especially if you have I/O intensive jobs where you've got other support in the hardware like direct memory access, where something that's doing I/O can kind of be parked off to the side and it can still do its work while some other processing takes place on the one and only core. But you're much better off to do parallel computing when you have lots of cores and or lots of processors. And the good news is that's the way the world's going at this point. So my laptop here has 8 hyper-threaded cores, so it's got 16 virtual cores, and it's very, very powerful. So that's becoming more and more common to have stuff like that. So that's the end of our overview of parallel programming concepts.